Welcome everyone to today's lecture on permutations and combinations, a fundamental concept.
In this problem, we'll explore the concept of combinations through the simplest possible examples. Having studied permutations in the previous video, we'll now learn combinations intuitively and visually. We want to seat these three boys in two identical chairs. Since the chairs are indistinguishable and order doesn't matter, this is a combinations problem in contrast to permutations. We'll now briefly clarify the difference between permutations and combinations. In a permutation setting, the two chairs are distinguishable. For example, they correspond to distinct posts such as president and vice president. This is a permutation problem because the seating arrangement depends on who sits where. Swapping the positions of the boys would result in a completely new arrangement. If C sits in the president's seat and B in the vice president's seat, that counts as one valid arrangement. If they move and change their seats, then that would create a completely new valid arrangement. This shows that order is important, as both who sits and where they sit make a significant difference. In permutation, both who and where they sit matters. However, in combinations, only who sits matters, not where they sit. The selection counts, the specific seats do not. Placing B in the left chair and C in the right chair counts as a single one outcome. This is one outcome. Now, if they swap seats, C on the right and B on the left, it does not create a new outcome, unlike in permutations, where it would. Our goal is to list all unique seating outcomes for placing three boys into two seats where order does not matter. Although this is a combinations task, we will first proceed as if it were permutations, since every combinations problem begins by considering permutations. Although our goal is to seat them in indistinguishable seats, we first treat the seats as distinct as shown to begin counting all possible combinations. Now we will first seat the three persons in these distinguished chairs and then reduce the count to the order does not matter case. We place the three pairs of chairs along the x-axis as there are three possible boys to seat in the president's chair. Then we show each respective boy sitting in the president's chair. This means that either A, B or C can sit in the president's seat, giving us three possible choices for the president's chair. Now it's time to fill the second seat, the vice president's. There are two other eyes available to sit in the vice president's seat. So we duplicate each of the seating arrangements, resulting in two possible configurations for each. For example, if A is seated in the president's seat, then either B or C can be seated in the vice president's seat, creating. Similarly, whenever B is seated in the president's chair, either A or C could sit in the vice president's seat, resulting in two possible seating arrangements for this scenario as well. Similarly, whenever C is seated in the president's chair, either A or B could sit in the vice president's seat, resulting in two possible seating arrangements for this scenario as well. Thus, for each of the three choices of boys for the president's seat, there are two possible choices for the vice president's seat. Altogether, this gives us 6 possible seating arrangements. And this is equal to permutation formula 3p2. Now it's time to revert to the original setup. We replace each distinguished chair with the original indistinguishable chairs. All the chairs are being replaced by the original ones. Now it's time to revert to the original. Now we group together the arrangements that seat the same pair of boys but only swap their positions. Now we group together the arrangements that seat the same pair of boys but only swap their positions. These two arrangements are identical in combination. Seat order is irrelevant. Only which boys are seated matters. Similarly, these two arrangements are counted as one. And these two are also counted as one combination. Since each ordered outcome has a mirror duplicate, so the 6 arrangements are double counted. Dividing by 2 gives the 3 distinct combinations. Now, let's visualize what dividing by 2 does. Each duplicated pair of outcomes collapses into a single unique combination. Look closely at the process. It makes the division clear. Each outcome was counted twice, so we correct by dividing by 2. And this illustrates that NCR is equal to NPR open R factorial. Each unique selection corresponds to R factorial ordered arrangements collapsed into one.